Okay. So thank you very much on that, and Luigi, for inviting me. This lecture.
Okay. Well, just a short introduction. Well, first of all, welcome to this course on graphical models. Well, this course is organized in the context of a PRIM project, this national project. There are 4 units in this project, 1 unit from Palermo, University of Palermo, University of Florence, Università Cattolica Milan, and here in Padua. Within this PRIM project, there is a short course organized, and then on Wednesday, there is a workshop. Always on the topic of graphical models, the workshop is going to be more in the area of biological metrics. As you know, the course is a 2-day course. Today, the teacher is Professor Abruzzo from the University of Palermo. Tomorrow, will be Professor Castelletti from the University Università Cattolica Milan. A couple of technical information. First of all, in the organization, we had thought of organizing a couple of coffee breaks. The course is going to be tough, I think, and a couple of coffee breaks are free. And so 1 in the morning and 1 in the afternoon. It's going to take place in the garden here. And then lunch is free. Okay, so there's nothing organized for lunch, and there are many places around as well. Okay, about internet connection, well, you have some information about the internet connection. Anyway, there is the usual EduROM network, but also a specific network, Wi-Fi network called Conveni. It is open, password is not required, so you can use that. Okay. Okay, just to wish you well.
Thank you, Alberto. Okay, so let's start. So I'm Antonino Abruzzo, I teach in Palermo, and I also teach graphical models, and I was talking with Alberto about let's say how difficult it is to teach a course on graphical. Somebody here as all my courses in Palermo, they know the trouble we have every time in understanding something. For me, it's like should be natural because it's kind of natural way of thinking. Okay, but when you put in mathematical stuff, it's going to be a bit small bigger. And not that. Lui che con that. Ok, allora uso questo. Okay. Not used to this. Okay. Can you hear me? Is it okay like this? Fine? Okay. So I was saying that so it's going to be a big point. Just try to not give anything for granted, and we're going to talk about some topic that should be there, but sometimes one forget about it. Okay. So first part, so first hour and a half, we are going to do an introduction. Okay. So if you have any question, please just ask whenever you want. You can stop me and ask. Okay. So first part, introduction. Then we are going into motivating examples, okay? And in the last part, we talk about a little bit about graph theory. But it's just not the graph theory we should study, but it's just to know the terminology on graph. Okay, stuff like neighborhood, parents, children, stuff like that. Have you ever heard about this stuff or not? Yes? So you have already followed something about graphical model? More or less? A course or studying yourself? By yourself. Okay, good. Okay, so what is a graphical model? What do you think is a graphical model? So there are two words, right? There. Model and graphical. So graphical doesn't refer to the plot, let's say, right? It's another stuff. It's called conditional independent stuff, okay, graph. Model, well, you know about model, right? Probabilistic models. So let's put it this way, we can, roughly speaking, say that in the graphical model, you have a connection between graph, conditional independent stuff, graph, okay, and probabilistic models. So you try to put together two words, graph and probabilistic models, that are kind of separated at the beginning, okay? So, and so you have this object, the graph, and the conditional independence. Have you ever heard about conditional independence? I guess so, right? Have you ever used conditional independence? I think so, right? Okay, but we are going to talk a little bit about conditional independence because we need that. Okay, so what is a graph? Who knows what is a graph? Somebody knows? Yes or no? Yes. Okay, it's an object, mathematical object, that has two things inside, right? What is inside? The nodes. Okay, these are just, let's say, dots in a space, and then the link between these nodes. What these links represents? What do you think the link between two nodes represents? Is a connection? Is a relationship? Or is something else? So you have, for example, a street, right? And two cross in a street, you connect two nodes. This is the street that connect A and B. This is just a connection, right? And it's a network, if you want. A network of the streets. In this course, we are going to talk about links that connect two nodes because there is a conditional independence assumption, or in this case, conditional dependence assumption. Let's go into detail by an example, okay? An easy one. Okay, so we have a problem. We have a burglary at home, okay? And this burglary can happen because, okay, there is, sorry, an alarm that sounds at our home if somebody tries to steal stuff from our home, so there is a burglary, or if there is an earthquake, okay? Terremoto e rapina. So you have earthquake and burglary, and then the alarm of our home sounds if there is one of these events, if one of these events happen, okay? Okay, so let's try to put it in graphical model term. What, in your opinion, are the nodes of this problem? I want to hear you. Okay, somebody can start. So you have nodes, right? There are 3 nodes. We'll tell you. What are these nodes for you? The alarm, the earthquake, and the burglary, right? So you have 3 nodes, right? The alarm, the earthquake, and the burglary, right? What kind of variables are there? These are continuous variable? No. These are discrete, right? Because they can take value 0 or 1. 0 is if the event doesn't happen. 1 if the event happened. Okay, so you have that this A, B, and E can assume value 0 or 1. 1, it means what? If the alarm is equal 1, that the alarm sounds. Okay, something happened in our home. Okay, what kind of assumption can we make on this example? Do you think that the burglary and earthquake are related somehow? Yes or no? No. And what does it mean in statistical term? They are not related. How do we interpret it? This symbol here, what does it mean? They are independent, right? So we just are making an assumption. This assumption is that the burglary and the earthquake are independent. And this is kind of normal for all of us. Are you agree with me with this assumption? Okay. So now this one here, what does is telling us? This means, do you know what this symbol means? By the way, yes, you know. Come on, come on. If somebody doesn't start, you are going to be like all the good day, and I don't like it. So, yes. What's your name? Yeah, Valentina. You are my victim today. So, Valentina, tell me. So this one, I'm too far. This one here. Huh? There is no, okay, so they are conditional dependent, right? So this means that the burglary and the earthquake are conditionally dependent on the alarm. Can you explain a little bit better? There is a text there, but I don't want to read the text. I don't like it. So I want that you start reasoning about graphical model, because it's not just math, it's reasoning about stuff, right? So Valentina, right? Okay, don't worry, I'm going to take other names, so it's not the old, it's just the first hour. Okay, so why did I put this kind of dependence there? Can you, don't read the text, can you just reason about it? Why they should be dependent? Come ti chiami? Luca. Valentina, are you in agreement with Luca? No. No, she's too kind. But I tell you, no, it's not. Why? Vicino Valentina c'è? Laura. Laura. So why Valentina disagrees with Luca? She doesn't like him? No, I don't think so. It's not that one. But, Laura?
So it's conditional independence or conditional.
Conditional dependent. This is conditional dependent.
So that and then
Uh-huh. Yeah, it's correct. Come on. It's there. Okay, so Laura's trying to tell us the alarm goes on, so it sounds, okay. So one of the two events happened, right? Because the alarm sounds if there is an earthquake or a burglary. Let's say I tell you there was a burglary, right? I'm giving some information about the earthquake, so this means the probability of an earthquake happened, right? Given these two variables change if I give you information about the burglary or not. Yes, it does change, right? Because you are less likely that there is an earthquake as well. And this means conditional dependent. Okay, see how it's just a simple example, but this tells you something about the Bayesian network at the end that we are going to build. Is it for Luca? Now it's clear what? So first of all, you have to start from what you condition to A. So this is your kind of variable that you kind of observe. But it doesn't mean that you observe it. It doesn't mean it happened this, and then you go behind. So on the other side, this is what Laura did, right? Is it correct? Did I misinterpret you, Laura, or?
Yes, yes, yes.
No, I didn't. I interpreted you correctly. Yes, okay. So for everybody's clear, this simple example, are you sure? Because I see some face that, what's your name? Huh? Claudia. Okay, yes. Okay, so can we go? Now, let's suppose we want to build a graph, which we know what is a graph, we said, right? And we build something, this is too much. Okay. I don't know why it doesn't show the graph. Something like this, okay? This one is it's called DAG, directed acyclic graph. And it has some peculiar stuff. This link between the two variables are arrows, okay, right? And this is called V structure. What this stuff here does is implementing the conditional independence and dependence we talked about in the slide we just seen. Okay, so this one here, if I give you now this graph, you have to interpret this graph as we did before. So this means that marginally the burglary and earthquake are independent, right? But if I give you information about the alarm, then they become conditional dependent, which is the second assumption, right? So this is what we are representing here. So the graph, conditional independence graph, represents what? Our belief on the conditional independence on the random variables we are giving for the problem. Okay? Is it clear? Questions for? Yeah. Oh, what an enthusiasm. No, it's 9 o'clock, okay, it's summer day, but yeah, okay. Okay, let's extend this problem. to something a bit more difficult. Now there are two new subjects. They're called John and Mary. John and Mary doesn't talk to each other, but they kind of call if the alarm goes on. Okay? Do they call that? Always no, because they kind of are distracted about something else. For example, John listens to the music to the headphone, so sometimes doesn't hear the alarm that goes on. Okay, so they call sometimes, but sometimes they doesn't call. What is this? A probability. So the probability if the alarm goes on, then John can call or not. Okay, it's likely that he calls, but he cannot also. Okay, what do you think, or where do you think, and how do you think these are connected with the problem that we saw before? First question, do you think that John and Mary are conditional dependent or not? They have a common cause, that's technical, right? More without technicality, what do you call it? It's common cause, so it's correct. He said the alarm goes on, so they call. Okay, but the question is, are these two conditional dependent or not? John and Mary. What do you think? You have 50% of chance of being right or wrong. He said no, right? Andrea said no, they are not. Valentina is like, Luca, also. Andrea. Independent. I said independent, right? So yes. Conditional independent. Why are you skeptical about it? There is a common cause, he said, and it's correct. So let's think about it. So if you remove this common cause, right? But the alarm goes on, and you don't know it. Are they more likely to call? You don't know the alarm, okay? That goes on. The alarm goes on. Are they correlated? Yes, because they call with more probability, right? Because you have this hidden variable, if you think about it, that you remove, but they go to call you anyway, right? It's more likely that they call you. So they are marginally dependent. Marginally dependent. That's what I ask, okay? Are you convinced now, Andrea? Yes? Yeah. Well, maybe I put the wrong question, but the marginally, sorry for that, but marginally they are dependent because the common cause, right? Okay. Now I condition on the alarm. They are okay. How do we represent this in a graph? You did it, right? Okay, the alarm is going to be the parent of two childs, which are John and Mary. So there is an arrow that goes from the alarm to John, and an arrow that goes from the alarm to Mary. Okay. Okay. So this is the graph. Yeah? How is it going? Good. Sorry for putting you there and then I go there. So I will try to pass by here. Is it clear so far? Yes? Questions? No? Okay. So what have we done so in these few slides? If you think about it, we just built a network from what? From our belief, right? So there is no data. Have you seen data here? No, right. So we just put conditional independence or dependence, we reason about it, okay, and we build a network. At the end, I would like that you try to reason. I will give you algorithm to learn Bayesian network from high dimensional blah blah blah. Okay, I shouldn't say blah 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 because we are recording, but anyway, the issue is interpretability of what we are doing, understanding what is in the graph. Because at the end of the day, if you collaborate with, I don't know, a doctor, right? Or a psychologist, or a epidemiologist, whatever you want, you show this one, and you need to explain it. They don't know about conditional independence, right? They want to hear you the explanation as we did now. Yes or not? And at the end, I hope in the last 1 hour and a half, I will give you 3 data sets, one per group. We make some group, okay? And you're going to work on this data set by your group. And then we extract 3 groups, okay? Just to present a little bit of what you have done. Okay, you select a graphical model, you work on this, and you present something. 10 minutes, no more. Okay? At the end of the day, if you survive, of course. Okay, so, but to do that, you need tools, right? Okay, so these are here you find the summary of what? Of the conditional independence. As for this, we talked half an hour about this, right? Can I go on? Yes. Okay. Let's. Well, I will go a bit faster here. So you have another example. It's a bit more complicated, but nothing more than what we have talked about. So this is a medical diagnosis. Graphical models are kind of used very much on this kind of problems. So you have flu, the variables are flu, hay fever, season, congestion, and muscle pain. Okay, so here you have 1, 2, 3, 4, 5. Some of them are binary variables. One of these is discrete with 4 categories. Okay, variable, which is season. And what I want to show here is the number of parameters that you have in this problem. How many? How many? So these are the product of what? Of the cardinality of each variable, right? So it's 2 times 2 times 4 times 2 times 2. So you have 64 parameters, which means you have a table, right, that you have to fill with 64 probabilities. -1, okay. But this is what you have, right? And the problem is going to be difficult, right? How can you assign 64 values of probability to all these variables, to the joint probability of these variables? So, one question that you can ask yourself is, for example, how likely is that the patient has the flu, given that it is fall and she has sinus congestion but no muscle pain, right? So, like, these kind of questions are very common, right? Because it's like when there was COVID, there's, how likely is that you have COVID? Based on what? On other variables that you observed. Okay. Here is the example that should show you the powerful of a Bayesian network. We haven't defined a Bayesian network. We will define it later. But we understand what is that, right? What are these? These are the nodes: season, flu, hay fever, muscle, and congestion. So it's like the season influence whether you have flu or a fever. The flu would cause what? Muscle pain and congestion, and the high fever cause congestion. Okay. Behind this, there are assumptions like the problem before, like this one: flu and high fever are conditionally dependent given season. But if I conditional congestion, flu and high fever are dependent, right? It's the contrary, because there is a V structure. Okay, but the point of this slide is more this one. This last bit. This is called factorization. Okay, so we said that we have 64 parameters to estimate or to give to the model, but if we use the conditional dependence assumption, then we can simplify the problem, right? Why? Because, well, this stuff here, okay, produce something in the factorization of the joint probability that reduce the number of parameters to estimate. Okay, so this is kind of, if you observe this one, is the factorization of the joint based on what is here, based on the parents of each node. So, for example, does its season has any parent? No, right? So you see that the probability of season is on itself, right? What is the parent of flu? Is season, right? What is the parent of high fever? Season. And you see here you have probability of flu given season and probability of high fever given season. And then you have congestion. What are the parents of congestion? Flu and high fever, right? And you have this probability here of congestion is this one, and then you have the last two. Okay? But the nice thing is that you reduce the number of parameters that you had before. It's from 64 to around 18. Okay? So in particular, okay. I didn't put here. Okay. And in particular, so this, what we have shown so far is that, so you have a graph, you use a graph as representation of, we say, conditional independence. So we start from conditional independence, we use the graph to represent the conditional independence. That's the first example, right? Second one, what we did, we use a graph to reduce the space, so the number of parameters that we need to estimate, which is, we use a graph to factorize the joint probability distribution. Yes or no? Laura is convinced, Valentina also. Yeah? See? Yes? Okay, questions? Can we go on? Yeah. Okay. Oh, this is a basic, right? Chain rule of probability. You all know this one, but I will not skip the details. So this one is, you can always write a joint probability distribution as a product of probabilities using the chain rule of probability, right? So this equality is true always. The question is, does it reduce the number of parameters to estimate? Yes or no? Andrea. So if I use this one here, right? Or I use this one here, have I reduced the number of parameters to estimate? Let's say these are dichotomous variables. So you have 8 values, right? 7, because 1 is given by 1 minus. But then, no, right? Because, well, this is not a reduction. There is no approximation, let's say. It's just another way to write the joint probability. But the number of variables that you are involved, if you see the last one, is 1, 2, 3, right? But what about if we reduce this one? Because there is conditional independence. Then we reduce the number of parameters to estimate. And this is the thing that I showed before about factorization, right? If we can make some assumption on conditional independence, we kind of simplify the stuff. But the factorization of the Bayesian network starts from the chain rule. Yes? Okay. So good. And this is other basic stuff, let's say. What does it mean to have X independent of Y given Z? The definition. It means what? That you can write the conditional probability of X, Y given Z as a product of X given Z times Y given Z. And this equality should hold for all values X, Y, and Z. This is the definition of conditional independence. So when I write this symbol, it's like you have to have in mind this equality. Yes or no? Okay. So if Z is empty, what is, if Z is not there, you see, is the independence without condition, right? The usual stuff. In the likelihood, when you use the likelihood, the first assumption that you make is that observations are independent. Okay, so you multiply, okay, by the number of subjects that you have. That's it. But that's independence. It's not even conditional. Okay. Last stuff that is important, and then we go a bit on theory of graph, is this one. So when you have a graph, let's say, you want usually answer to queries, questions. Like in the flu example, do you have flu? What is the probability that you have flu? But it could be that also it's not the flu the object of my my question, but it's something that is above or on the, let's say, not above the flu, let's say, okay? So it's something that is over. And you have something caused by the flu, but you want to infer something that is here. For example, in the alarm, right? It may be that Mary calls, okay, and you want to know the probability of an earthquake. And you say, how they are related? Do you see the relationship? So if I just tell you what is the probability of earthquake if Mary calls, you like, okay. But if you think about the graph, there is a path between what? Earthquake, alarm, and Mary, right? Why Mary calls? Because the alarm goes on. Why the alarm goes on? Because there was an earthquake. So sometimes the query is on the, let's say, central variable, the outcome, the one that in a regression problem you would put as y, for being clear. Sometimes it's not that one, but it's something that is above all in the child, okay? In the descendant, let's say, in the graphical model speaking. This is clear? These are queries. And you answer queries once that you have built what? So to answer a query, like the one that I asked before, probability of earthquake, given that Mary calls, what do you need? Data. Okay, but what do you need to build in order to answer that query? What do you need? We will talk about model later. Sorry for that. A graph, yes, and we have a graph, right? Because we did the graph, we show the graph, but what do you need actually? R, for sure, no. The joint probability distribution. If you have the joint probability distribution, you can answer all queries you want, right? So if you have a marginal probability, let's say you have two variables, right? And you have the marginal of A and the marginals of B. Can you answer all the queries I ask about the problem? No, because you need to fill the table inside. What are these numbers inside the table? These are called joint probabilities of A and B. So if you have a table that is bigger than this, you need to fill all the 64, right, points in the big table. And then you can extract the query by conditioning on the evidence, it's called evidence, and then marginalizing by the variables that you don't need. That is what answers the queries, right? Is it clear? Yes. Nome? Name? Pietro. Yes.
The instantiation E, does it mean that is the location of an app?
So this, where is that?
It's just word that.
And there is instantiation. Yes, it's like it's evidence. It's a synonymous for evidence. So instantiation means that Mary calls. Yes. So Mary calls. You know that she called. Okay. And that one is an evidence, an instantiation. You put something. Yes. Yes. It's like you have a patient. You give aspirin. Okay, you give him aspirin, and then the probability that he is feeling better is, yes? Okay, this is it's evidence, okay? It's just a fancy word in the slide, don't worry. Okay, good. Clear? Shall we go on? This is a bit, it's going to be, I don't know, For me, it's like always a bit boring this part, but you need some terminology. Sorry for that. So this is put mathematical stuff there. Okay, so you have a graph G, which is with two objects, V and E. V, we said that are nodes, or they are called also vertices. Okay, and then you have this epsilon or E, well, will represent as whatever you want, is a finite set of links between the nodes. Okay, so if you have in the set, the link between these two nodes is present, otherwise it's not. Yes, and you have two kind of graphs: undirected graphs and directed ones. The directed ones, we saw that, right? And they have arrows between nodes. The undirected ones, they connect these two nodes, okay, but there is no arrow. Okay? There is like, I don't know, in the directed case, it's like you are almost reasoning causally. There is something, okay, something happened, and then this something that happened, the earthquake caused the alarm. But this is just for you, okay, because causal graphical models are something else. They require some additional assumption, which we don't see here. Probably you will see something on Wednesday, okay, on causal graphical models. So to show causality on graphical models is not the Bayesian network we are talking about, but it's just to understand, okay, to have the feeling. It's like when you do regression. Why conditioning on x1, x2, x3, x4? Are you saying that x1, x2, x3, they cause y? No. It's not a causal model, right? It's a regression model, which is not causal. It's different. Instead, in the undirected graph, you have to look more at correlation between two nodes. So it's something that goes together, okay? We will make an example in the third part. Okay, so then, okay, we talk about directed acyclic graph. What does it mean, acyclic, by the way? Acyclic means that I cannot go from one node to itself in a finite or infinite number of steps. So I cannot go back from Mary to from earthquake to earthquake. Cannot go there. And the limitation there is related on the factorization, actually. Because if you have this recursive graph, then you cannot use anymore the factorization. Think about it. The probability cannot be factorized anymore. And then it's a big problem, okay? So we just reduce ourselves in the class of directed acyclic graphs. And these are the kind of words that they use: parents, children, path, ancestor, and ancestral. Okay? So parents, what is a parent? It's like genitori, no? So it means that the node I goes to the node B, let's say. Okay? Earthquake goes to alarm. Earthquake is a parent of alarm, but also burglary is a parent of alarm. So the set of parents of alarm is made by earthquake and burglary. Yes? The children of alarm are, do you remember the graph? Mary and John. So these are the children, right? Okay. The path is, for example, from earthquake to Mary. There is a path. Why? Because I can go from Mary to earthquake, true, alarm. Do you remember the plot, right? Okay. Then we have the ancestor. Well, here, for example, for nodes 4, the ancestor are here. So all the nodes that are above, let's say. Okay? Antenati. Yeah. Well, this is more or less about it, about the directed acyclic graph. For the undirected ones, we have different terminology, but it's kind of intuitive. So the intuition helps in this case. We have two nodes that are neighborhood, okay, or adjacent. The closure of a node, subset of a graph. This is a bit more difficult, maximal click. We will look about it. And then we have a path and a separator. Okay, we will talk about this topic. Right? In the meanwhile, do we have questions about it? No? It's fine. Good. Okay, so okay, this is an undirected graph, right? You see the nodes. Yeah, you cannot see the numbers here, but let's imagine there is 1 here, 2 and 3, okay? So you said they are adjacent or neighborhood when there is a link, when there is a connection between the two nodes. So let's say 1 and 2 are neighbors because there is this link, okay? But 1 and 7, they are not, okay? And the neighborhood set of 1 is the set of all adjacent nodes of 1, okay? And so on. So this is very easy. For example, for 7, which is this node here, it doesn't have neighborhoods, so it's an isolated node. And this means in terms of probability, that its probability doesn't change whatever happens in these 6 nodes. So it's like marginally, conditionally, whatever independent. So you can treat it as itself. Yes? Okay. The closure is like the neighborhood, but you have to add the node itself. So if you have 1, okay, you kind of, sorry, this one, for example, you add this one, and this one. These are the neighborhoods of this node, but you need to add also this one. And this is the closure of the node 1. Okay? This is a subgraph. So you select a subset of nodes and you take the connection of these nodes. This is subset. Okay? And the graph, resulting graph is called the subset of this graph. Okay. Well, these are examples. Okay, and then you have the click. What is a click? Somebody has heard about click? Huh? Okay, technically it's a subgraph which is complete. A graph is complete if it is all connected. So if all the nodes are connected, then the graph is set complete. So a click is just that one. So if I set a click of this one, it can be, for example, these two nodes here. Why? Because if I take these two, 1 and 2, let's say, if I take just this one from this, are they forming a complete graph? Yes, because they are connected, right? But if I take this, and this node here out of this, is this a click? No, because there is a node that is not connected. So the subgraph that I form is not fully connected, and so it's not a click. The maximum click is instead a click which is not anymore a click when I add a node. So I need to extract the maximum of click. So I take the subgraph. I node. This form a subgraph which is not complete. Okay, I do for all of that. Yes? And then I say, okay, this is maximum. I cannot put any other node without making it not a click anymore. Yes or no? Okay, let's try to see whether this concept is kind of clear. Let's look at this graph and see, let's say that this is 1, 2, 3, 4, 5, let's go in this direction, okay? How many clicks do you think are there? Andrea?
Like 8 plus any couples.
Good. No, it's good because I said click, not maximum. Very good. Maximum click. Very good, Andrea. Now maximum, yeah? So count less. Yeah? So is this a click, for example, 1, 2, 1, 2, yes. Is maximum? No. Why? Because if we have this 3, then we find a subgraph that is complete, right? So we need to add this to the first click. Is it correct? Yes. Okay, let's add another node. Whatever you want. This one, for example, is, so if I take 1, 2, 3, 4, this one here, is it a complete graph? No, right? Because this node here is not connected to this and neither to this. So it's not complete. And if you do whatever you want with the other ones, you cannot add one more node without forming a subgraph that is not complete. It's correct? Yes? Okay. So that one is going to be our fast click. Agree? Yes or no? See, Andrea? Maximum, yes. Okay, from now on, let's say click to intend maximum. Yes. Otherwise, it's like, okay. Yes? Okay, second one. Can you help me with the second one? No.
Square.
The square, yes. The square. Yeah, right. So it's this was 3, 4, 5, 6. Let's say. This one, can you see it now? It's the second click. Okay. The third one, almost there. Come on, the break is coming, don't worry.
Watch if you triangles right.
Very good.
Why don't you triangles on the upright?
One of the triangles, yes.
Both.
Both are clicks. So we said that there are
Okay.
4 clicks. Yeah, correct. So we said, name?
There
Enrico.
you go.
Enrico. Enrico.
There you
Inglese, britannico. Accento non sembra. Okay, so this one is the other click, and this one is the other one. So we have 4 clicks. Yes, Max. Okay, good. Okay, you find it like nice picture. So when you look for paths in the undirected graphs, of course you are not going to have one path, right? If I said there is a path for, sorry, I don't know why it skips the name of the variables. Anyway, so this was V1, okay, and this was V12. Is there a path between V1 and V12? So it means I can reach 12, okay, in a number of steps. Yes, because I can reach it from here, right? Yes. Or I can do this one. Or I can do, I don't know, this one. Depends, whatever I want to go. Okay, but this is a path in the undirected graph. Here, with respect to the directed one, the direction doesn't count because we don't have a direction, right? Okay. Separator. So here it comes the fact that we have different paths. So if we can block all the paths between two nodes, the nodes that form the block of this paths are the separator, forms the set of separator, okay? So I have to take all to separate, let's say, A from B. Oh, the separation can be from one node to another node, or can be from a subset of nodes to another subset of nodes. For example, here, I can separate, for example, this here, let's call it A, from this one here, let's call it B. And in order to block all the paths between A and B, I need to block here this one, C. Okay? This is called the separator of A and B. And here is, well, the example is on a subset of nodes, not on a single node. Okay, yes, tell me.
Can you go back to the previous
Yes,
slide?
sure.
Okay.
Yeah, it will go at some point. Sorry. Yep.
So here, if I want like to separate A and B,
Yeah.
I can just, for example, I can just remove B4. If I remove B4 from the graph, A and B are not.
Yeah, I
They
understand
cannot
your
be
point.
connected. So B4
Thanks.
is a separator or not? Because
It's not the separator as we define. Because in the definition of separator, we have every path intersecting A and B. So it's that one is not the set of path. It's just one node on the set of path. Yeah. The thing that you say is kind of if you condition on before, then you don't need information about the other ones. But that's another story.
Yeah,
Yeah.
because all the paths connecting them pass through
Yeah.
B4.
Yeah.
Or,
Yes. Yeah. Or even the last one. Yes. Okay. So this concludes kind of the introduction. I will give you something about, well, history now. Let's move a little bit, and then we take a break after this one. On the, well, where they come from, the graphical models. Let's say they come from these guys. One of these is them is Lauritsen. So it's very famous. I don't know whether you have tried to read this book. Very good. And the other are Dempster, Dempster and Darrow. But this is where they kind of start in the, well, with problem with contingency tables. So when they start to be a little bit bigger and bigger, then you cannot just work with that. And so you need some kind of introduction on conditional independence assumption, because we say, okay, they reduce the complexity of our problem, right? And if you look at the first paper, like introducing it in contingency tables, is this one, introduces the 80. And then we kind of move, well, this was before actually, in the continuous case, okay, in this short course, at least in my part, we will talk always about discrete graphical models. So these are graphical models for discrete random variables, so contingency tables. But you will have also the continuous part tomorrow, and they kind of were born trying to simplify the covariance matrix of the normal distribution, okay? Because, well, you can show that the inverse of the the covariance matrix in the normal distributions give you information about the conditional independence. This is called precision matrix, by the way. And, well, try to simplify this stuff will simplify your conditional independence, so your problem, in a way. And this is was called covariance selection problem. And then, well, there was this extension, try to kind of mix the discrete case with this continuous case, which is very hard, actually. And this paper is the one of Lauritsen, which extend the graphical model to the discrete and continuous case. Okay, these are all cited over there. Then we have the other story with Perl and Vermouth, which is more on computer science, let's say. In particular, Perl use something like it's called the do operator. I don't know whether you have heard about, but it's related to the causal stuff that I was talking about before. Okay, but we are not going there. And just to know, let's say more recently, but this has been already many years. It's more recently when I started my PhD, let's say, so many years ago. We have kind of this problem with high dimensionality. So nowadays the problems are high dimensional. So we have a lot of variables, and in the graphical model world, the high dimensionality goes it's come very fast, let's say, especially in contingency tables. There you have the sparse table problem. Think about a contingency table. You have 6, 7 variables. You have to fill all of this with all the combinations of the categories that you have for each variable. So it becomes 0, 0, 0, 0, 0, 0, 0, 0 everywhere. Okay, so this is a big problem. In this stuff that I mentioned, this is more for continuous stuff. The high dimensionality is related to the number of parameters that you have to estimate in a covariance matrix problem, which becomes very high, well, with, let's say, 1,000 variables. And let's say, first attempts were by using shrinkage on the likelihood. So it's like lasso, stuff like that, by Friedman and other. And then you have these 3 papers there. Finally, well, the applications, I think there is much more to do about applying graphical models to real problems. If you try to look at papers on application of graphical models, you won't find a lot of papers. You will find a lot of papers about theory, but much less about application. Why? I don't know. I don't know yet, but you can start applying, right? Now that you finish this course, then you can start. But the applications are on genetics nowadays. You have gene-gene interaction problems, for example, where you use a lot of graphical models, finance, tourism, psychologists. Okay. Just a couple of minutes on this. We are going to use R. You are all familiar with R software? Yes. And there are a lot of packages on graphical models. Like GRBase, GRIM, iGraph. This iGraph, for example, is dedicated to picture nice graphs. Okay. And then we will use BNLR, Bayesian network learning, for learning Bayesian network. We are not going to use GLASSO or Huge, and the other ones, yes, GRBase. The nice thing is, since we have a couple of minutes, you have also a task view in R. Okay. Which is this one. Oh, oops. Can you see it? Yes. Okay. So this page is dedicated to graphical models. You will find the packages and some explanation about the graphical models, even the definition from Wikipedia, but let's see, leave it there. So you have the package at the beginning and what it does there. For example, iGraph is a routine for simple graphs and network analysis, okay? The Bayesian network is here, somewhere. Exactly, here, okay? So here you can have a look, whatever you want, and take stuff from there. Another nice thing, I don't know whether you have ever used Bugs. It's a software. No? WinBugs, OpenBugs. Okay, Bugs is a software that helps you to do, let's say, Gibbs sampling, metropolis testing. And in WinBugs, there is a section in which you can build your model as a network, Bayesian network. So, I don't know, imagine, well, Y is normally distributed with mu and sigma square, univariate, okay? So, and you want to put it in Bayesian network. So you have Y, right? Which depend on what? Mu and sigma square. Mu and sigma square will become what? The parents of Y, okay? If you want to build a hierarchical model, for example, you want to put some prior on mu, okay? You just put something above mu, and these are going to be the parents of mu. So WinBugs has this tool which is based on Bayesian network. So it's very, very nice. Okay, so I think we can yeah, we can stop here and take a break, right? Time to break. Do you have any question before going? So in the second part, we are going to talk about Bayesian network. So the idea is to have 1 hour something theoretical. And the last, I will show you an example of application on the Bayesian network. Okay, so this is the second part. Do you have any questions? You sure? No, yes, no. Okay, take 4 coffees because we need that. And we see in half an hour. In 2 hours.